Module 15, Chemical Equilibrium, Temperature and Le Chatelier's Principle. It's time to look at one more change that can affect equilibrium, temperature. To discuss the effects of temperature, you need to remember that when a reaction is exothermic, its change in enthalpy is negative. That means that energy can be thought of as a product of a reaction. If a reaction is endothermic, then the change in enthalpy is positive, and energy can be thought of as a reactant in a reaction. Look at this equilibrium reaction. We are told that change in enthalpy at standard conditions is 242 kilojoules. Because it is greater than zero, it is an endothermic reaction, and we can think of energy as a reactant in the equation. With energy a part of our reaction, it will be easier to think about what happens when we change temperature. What are we doing when we raise temperature? We're adding energy, aren't we? So when we raise the temperature in this reaction, we are technically adding reactant. You should know what happens to an equilibrium reaction when we add extra reactant. The forward reaction increases its rate, and more products are formed. Less reactants result. So when we raise the temperature, the reaction will shift to the product side. More hydrogen and oxygen are made, and more water is used up. Now, what if we were to lower the temperature? It's like removing a reactant. That causes the rate of the forward reaction to slow down, which makes the reverse reaction faster than the forward one. This means the reaction will shift to the reactant side, making more water and using up more hydrogen and oxygen. We can sum these ideas up by saying, when temperature is raised, an equilibrium will shift away from the side of the equation that contains energy. When temperature is lowered, the reaction will shift toward the side that contains energy. Module 15, Chemical Equilibrium. Experiment 15.2. This experiment will help us to explore equilibrium and how it works with temperature and concentration. So we want to get some indicator solution set up first. So I want to fill a pot with some water. About 200 milliliters of water is all we need. Not a lot of water. And some red cabbage leaves. All right, so we want those to begin to boil. So I have the temperature on high to get that water to boil. And while we're waiting for it to boil, we want to prepare the rest of our materials. So we need to get a small amount of ammonia solution and pour it into one of our cups. This is a new one. Don't inhale over the cup because it's very strong. The fumes are very, very strong. Mark that cup in a way that you know that that's your ammonia cup. And then do the same thing with vinegar. Okay, now we want to take the larger beaker that we have and fill it with ice water. And you want it to be mostly ice and a little bit of water. I'll show you that. We want it to be very cold and to stay cold for the duration of our experiment. I'm going to set that on my tray. Okay, and now we want our smaller beaker, about 3/4 of the way full of water, and we're going to get that water boiling as well. And I'm going to use my alcohol burner to get that boiling. And again, be very careful when you're using alcohol burners. Make sure you have the cap handy if you ever need to turn that water or that flame off. Okay, so that's starting to boil. Now we want to take 20 drops of the cabbage water once that's completely boiled, and put 20 drops into each test tube. So let me check on my cabbage water. So mine has a beautiful purpley blue color. And you want to put, I'm going to put it down into the sink just for temperature's sake. I want to put 20 drops of cabbage water into each of my 2 test tubes. If you don't have a test tube holder, just use another cup to hold those test tubes for you. Okay, almost this one. Do that to this one. Okay. All right, so I have 20 drops of cabbage water in each of my test tubes. You can see the color. Note the color is kind of a bluish color. I'll hold it up to this white napkin so you can see that. It's kind of a bluish color. And you're going to be paying attention to that. With each addition of material, you want to note in your textbook the color, or your notebook, the color of the liquid that's inside your test tubes. Okay, so now I'm going to rinse out my eyedropper. Make sure all that cabbage water's out of it. And I'm going to add 15 drops of vinegar to each of the test tubes. So this was my ammonia solution, this is my vinegar, and I want to add 15 to each test tube. Okay, I'm going to swirl these test tubes around. Remember, they have the same material in them. And notice how they're both pink now. The indicator solution identified an acid, and in the presence of an acid, this cabbage water indicator turns pink. That's what we should expect. Okay, now I'm going to take the other eyedropper, and I want to add ammonia to one of the test tubes. And I want to add just enough so that it just barely turns green. I'm going to swirl my test tube after each addition of ammonia drops. So get that in there, swirl, drop and swirl, drop, swirl it around, drop, swirl it around, just until the indicator solution changes color and turns green. I'm already noticing it turning a little less pink. Oh, almost there. And you can see it's a greenish color now. So I'm going to do the same thing with the other test tube. Adding ammonia, 1 drop at a time. And swirling after each addition. And there it goes, just until it turns green. Now both of these beakers have approximately the same shade. Actually, this one's a little bit blue. I'm going to put 1 more tiny drop. To get it more green. I want them to be almost the same shade. There we go. Okay. Our next step, now you can see our water is almost boiling. And I want to move my test tube rack. Take both of the test tubes out so you can see this. I'm going to put both of the test tubes in my ice water solution and let them get cold. And after sitting there for about a minute, I want to compare them and look at their color. Okay, now that my water is boiling, I'm just going to go ahead and turn off the burner. But that water will stay very hot for a while. Okay, let's look at the color of the test tubes in the cold water. And you can see they're both about the same color of green. I'm going to put them back in the cold water, but this time I'm going to put one of them in the hot water and let it sit for a minute. We're going to see what happens. I move it around just a little bit to expose it to that heat. You want to let it sit for about 30 seconds. You could keep the water boiling if you wanted to, so that you could, so that you could keep that water really hot. But it works this way as well, and I'm doing this so you can see it better. Okay, now let's compare. I'm going to take both of them out of solution and compare the colors. Let me drip off the edges there. Okay, this one right here is the hot, and this is the cold. And take a look at the colors. It's a little bit subtle. But the one that was in the hot solution is blue, and the one that was in the cold solution is green. I'm going to put them both now in the ice water again. And while I'm waiting, I'm going to get this water boiling again. We want our water to stay hot. Let these sit in the ice water together for 30 seconds again to cool those temperatures down. And you'll notice they're both the same shade of green again. One more time, I'm going to keep one in the ice water and one in the hot water for 30 seconds. When you're handling the test tube that's in the hot water, make sure you're holding it from the very top edge so you don't burn yourself. Always be very intentional and careful when you're doing this. All right, so now you pull these out, cap my heater, and notice this one right here was in the hot temperature. This one was in the cold temperature, and the hotter temperature one is kind of a pinkish blue, and this cold temperature one is green. So when you're done with this, clean everything up and put it away, and I'll explain it in the next section. In the previous experiment, ammonia and vinegar were mixed in test tubes, causing this reaction to occur. Ammonia aqueous plus aqueous acetic acid and vinegar react to produce aqueous ammonium ion plus aqueous acetate ion. This is an equilibrium that is heavily weighted toward the product side of the equation. So we could really show that like this. But there are still some reactants present. When you added cabbage water, you were adding an indicator that could tell you how much acid or base was there. When the test tubes had just cabbage water and vinegar, the mixture turned pink, indicating the presence of acid. When you added ammonia to the test tubes, the color eventually turned green, showing that the acid was neutralized by the basic ammonia. Now, this is an exothermic reaction, so we can add energy to the product side. When you put one test tube in ice water, you were lowering its temperature. That's like removing a product from the reaction. Therefore, the reaction shifted toward the product side of the reaction to relieve that stress, making more products and using up more reactants. The color of the solution turned greener. When the other test tube was placed in the boiling water, you raised its temperature, or technically added product. That caused the equilibrium to shift to the reactant side of the equation, making more acid and base. The color of that solution changed to reflect that. So this experiment was a great way to observe the effects of temperature change on a reaction in equilibrium. The cabbage water enabled you to see the relative amounts of reactants and products. If it was pink, there were more reactants, and if it was green, there were more products. Lowering temperature in this exothermic reaction was like removing product, so the equilibrium shifted toward the products, and the solution was greener. Raising temperature was like adding product, so the equilibrium shifted toward the reactants, and the solution was pink. To make sure you understand this idea, look at an example with me. For the following equation, hydrogen gas plus fluorine gas react to produce 2 hydrogen fluoride gas. The change in enthalpy at standard conditions is negative 273 kilojoules. If the reaction has already reached equilibrium, what will happen to the concentrations of each substance when the temperature is raised? This is an exothermic reaction because the change in enthalpy is negative, so we can think of energy as a product of this reaction. When temperature is raised, an equilibrium will shift away from the side that has energy. Raising temperature in this case is like adding products, so the reaction will shift toward the reactants. That means the concentration of hydrogen fluoride will decrease, and the concentrations of hydrogen and fluorine will increase. What will happen to the concentrations of each substance if the temperature is lowered? When the temperature is lowered, an equilibrium will shift toward the side that has energy. It's like removing product from this reaction, so the equilibrium will shift toward the products. Therefore, the concentration of hydrogen fluoride will increase, and the concentrations of hydrogen and fluorine will decrease.